we have bundled up 170 steel wires like this, each 3 millimeters in diameter. And now the steel wire bundle is put into a coil. Both of these are coiled 100 times. One of the coils is connected to the 3-volt battery and the other to the galvanometer. We'll call the coil connected to the battery the primary coil and the other the secondary coil. As I mentioned just now, the primary coil is connected to the battery with a switch fitted in between. Please remember that the primary and the secondary coils are not connected by the leading wire. The secondary coil is connected to the galvanometer. Now, leaving things in this condition, let's turn on and turn off the switch of the primary coil. Do you think something will happen to the secondary coil? Well, it seems to be moving slightly. Let's now narrow the space between the coils. How is it now? If we send a current on the primary coil or turn it off, a current takes place on the secondary coil. This phenomenon is termed electromagnetic induction. Let's now narrow the space between the coils even more. If the space is narrowed, the indicator movement increases a little bit. It means so much more induction current has been generated. Well, this time we change the secondary coil to one coiled 200 times. Now what's going to happen? Well, what do you think will happen now? The indicator movement hasn't changed much, has it? Well, do you think the indicator movement will increase if the space between the coils is narrowed? Ah, that's right. The indicator movement has become larger by narrowing the space between the coils. Now we'll try and see what will happen if we change the secondary coil to one with a greater number of windings, say one coiled 400 times. Well, what do you think will take place now? Here, you see, the secondary coil with a larger number of windings helps to generate greater induced current, doesn't it? We have so far been using a bundle of steel wires as an iron core. Let's now change it to an iron plate. Do you think something alike will take place this time? Well, let's see what will happen. Aha, the same has happened with an iron plate, hasn't it? Now, watch carefully. We are going to narrow the space between the coils again. Here we are. A greater induced current has occurred by narrowing the space between the primary and the secondary coils. would be the result if we put the iron cores of the primary and the secondary coils together. I wonder if the indicator oscillation has become a bit larger. Now let's link the upper ends of the iron cores. Now we'll see what's going to happen. Oh, that's great. The indicator is swinging as far as it can, isn't it? We'll change the 3-volt battery of the primary coil to a 1.5-volt battery. Even the 1.5-volt battery generates such a large induced current. Do you think we can obtain even larger induced current by narrowing the space between the coils? Well, we have learned from these tests that the induced current will change depending on the number of coil windings, the length of space between the coils, and the layout conditions of the iron core. Well then, let's change the power source to that of the alternating current. This time, we'll study the induced electromotive force by linking the secondary one, coiled 400 times, to the voltmeter. We put 10 volts pressure on the primary one, coiled 100 times. At this time, the voltage of the secondary one, coiled 400 times, indicates the figure of 40 volts, which is 4 times stronger. If the primary coil voltage is increased to 20 volts, the voltage of the secondary coil goes up, also 4 times, to 80 volts. The primary coil voltage is further increased to 30 volts, and the secondary coil voltage rises to 120 volts. From these examples, we learn that induced electromotive force is proportionate to the ratio of the number of windings of the two coils. Then, what will happen if the primary and secondary coil positions are changed? What do you think the result would be if tested under these conditions? We've got 2 coils here, the primary one coiled 400 times and the secondary one coiled 100 times. 20 volts on the primary coil and 5 volts for the secondary coil. That's 1/4 of the primary one, isn't it? We increase the primary coil voltage up to 80 volts and the secondary coil up to 20 volts. That's 1/4. In this way, the induced electromotive force is decided depending on the number of windings of the primary and the secondary coils. This principle is applied to the transformer. Now we'll come back to one coiled 100 times for the primary coil and 400 times for the secondary coil. We'll now use a 2-phenomenon oscilloscope to visualize the tests we have made so far. Channel 1 is connected to the primary coil. And channel 2 to the secondary coil. Channel 1 is connected to the output of the power source. The channel 2 to the voltmeter. We charge 20 volts pressure on the primary coil. These are the alternating wave patterns of 20 volts on the primary coil. These are the wave patterns of the secondary coil. We'll now see both of them at the same time. Next, we change the primary and secondary coil positions. The primary coil is given the pressure of 80 volts. These are the alternating wave patterns of the primary coil with 80 volt pressure. These are the wave patterns of the secondary coil. Now we'll see them together at the same time. Here on the same screen, we can learn the relations of each aspect of the tests more easily. This is the case where the primary and the secondary coil positions have been changed. This is a hydropower station operating in the depth of a mountain. The electric power generated at this power plant is given higher voltage at the closely located substation and is sent to the consumers. A transformer increases the voltage. Voltage should be increased in power transmission because power transmission to distant localities can be done with greater efficiency with higher voltage. The transmitted power first goes to the transformer substation near the consumer areas. Voltage is appropriately lowered here before supplied to consumers. Today, electric power for consumption is easily available anywhere because electromagnetic induction has enabled us to effect efficient power generation and transmission. Electric power, transmitted with the voltage of 6,000 volts, is lowered to an appropriate level by this transformer and then is supplied to every household and other consumers in general.